is the second lecture on the numerical solution of ordinary differential equation. In the first class, we have described what different Runge-Kutta methods or Runge-Kutta methods of different orders. This is the Runge-Kutta method of first order, while y1 is given by y0 plus k1, where k1 is this. This is the slope of the fx0 y0 is slope of the function at slope of the unknown function at x0. Then we go to Runge-Kutta 2, Runge-Kutta 3 and 4, which we have defined as the best method of the lot. And the error involved in the method, here the error involved is of the order of h square. Then in Runge-Kutta 2 it is h cube. In Runge-Kutta 3 it is of the order of h to the power 4, and in Runge-Kutta 3 order is of the order error is of the order of h to the power 4, and in Runge-Kutta 4 the order is of the order of h to the power 5. We have used all these four methods to solve this differential equation and show how the result improves as the order increases. In this method, x0 is 1, y0 was 2, and we obtained x1 is equal to 1.2 and obtained the solution like this. So the summary of our result of last class is that x1 is equal to 1.2. The corresponding y1 is 2.9284 as obtained using RK4 method. Now we want to extend this to find out the value of y at x is equal to 1.4 or 6 like this. So for the evaluation to determine y2 is which is y at x is equal to 2 is equal to y at x1 plus h. We are to again apply this method, but here the starting point will be x0. So first thing is we to calculate k1 is equal to h f of x1 by 1. And the function is again h is 0.2 and x1 in this case f of 1.2 and y1 is 2.9284. that is the function. Recall that function is this 0.2 times 2 times 1.2 plus 2.9284 and the result is 1.06568. Then come to K2. K2 is h f of x1 plus h by 2 y1 plus k1 by 2, and this is h f of x1 is 1.2 and times h by 2, so this is 1.3, this part is 1.3. We have y1 as this and k1 is this, and if we divide it, ultimately it is found to be 3.4646124, and the result is 0.2 and 2 into 1.3 plus 3.46124, and the final result is 1.11 1.112248. This is the value of K2. Now coming to K3. K3 is h f of x1 h by 2 and y1 K2 by 2. And K2 value is known. So this is again h times f of 1.3 and this part is 3.5345534524 and on utilizing this we get it as 1.22 and finally K4 so this is h times f of 1.4 and this part is h1 plus K3 is 4.155 3048 and on simplification this becomes 1.39 106096. So y2, that is y is equal to y1 1 upon 6 k1 plus 2k2 plus 2k3 plus k4. You see that the values of k changes from step to step and this comes out to be 4.15090090776. Now we can use these values of y. This is the value of x2 is equal to 1.4 and y2 is this to calculate y3, that is y at x is equal to 1.6, and by this way we can proceed from one step to another step. And to have convergence or check for convergence we are to check h values. Or we are to reduce y values to see how the we are to reduce h values to see how the corresponding y values changes. If the change is within acceptable range, then accuracy is said to be achieved. Now we shall turn over to numerical solution of a set of two simultaneous equations. You recall the Runge-Kutta-4 method for a single variable is this. So we write the summary RK4 method. We shall solve two simultaneous equations, first order simultaneous equation using RK4 technique. Numerical solution of two first order differential equations. So the equations, let the equations be dy dx is equal to f of x, y, z and dz dx is equal to g of x, y, z, and with the conditions that with y at x0 is equal to y0 is known, z at x0 is equal to Z0 is known. This is the. Now, if we try to solve the first equation, then we first calculate this function. For a single variable, we have calculated this as the. But here, the f and g are functions of x, y, and z. So we first redefine k1 is h f of x0, y0, z0. Correspondingly, here we define L1 is equal to h g of x0, y0, z0. Now we come to k2. K2 is h f of x0 plus h by 2, y0 k1 by 2, z0 plus L1 by 2. This is K2, and correspondingly L2 is obtained with same argument, but the function changes. You see, since the equations are simultaneous, the evaluation of K2 or K2 also requires the knowledge of L1. Similarly, evaluation of L2 requires the knowledge of K1 because they are not disjoint equations. They are coupled equations. Now we come to K3. Similarly, h f of x0 plus h by 2, y0 k2 by 2, you recall this, z0 L2 by 2. Similarly, L3 is equal to hg x0 h by 2, y0 k2 by 2, z0 L2 upon 2. And finally, we calculate K4, h f of h x0 plus h, y0 plus k3, you remember this one, z0 plus L3, and L4 as h g0 x0 plus h, y0 k3, z0 3. So this is the method. All k's and l's are obtained. Finally, we use this technique to evaluate y and z at. So y1 is y0 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4, and z1 is equal to z0 plus 1 upon 6 L1 plus twice L2 plus twice L3 plus L4. So we get the, knowing the values of the function of x, y, z at point 0 starting point, we can land up to the corresponding values of y and z at x1. If h is sufficiently small, the y1 and y1 and z1 values are accurate enough, then using this y1 z1 value we can get the values of y2 z2, and we can proceed in this manner. We want to apply this method to a specific problem. We choose as an example, these things are known, so we can, so as an example we use f function. F is, this is equal to x plus y plus z, and this function is 2x plus 3y plus 4z with y at x is equal to 1 is, sorry, y at x is equal to 0 is 1 and z at 0 is 2, and we are to find y at 0.2 and z at 0.2. So we have x0 is equal to 0, y0 is equal to 1, z0 is equal to 2, and h is equal to 0.2. So first let me calculate k1. So this is h, f of 0, 1, 2. You know the function is x plus y. So this is 0.2 multiplied 0 plus 1 plus 2. So this is 0.6. No, the example that is being worked out is slightly different. So it is 2. So this is then come to L1. You know the function is 2x, so this is 0.2 multiplied by 2 into 0 plus 3 into 1 plus 4 into 1. So the this is 1.4. Now come to K2 evaluation. K2 is h, f of x0 plus h by 2, y0 plus k1 by 2, z0 plus l1 by 2. So this is h, x0 is 0 and this is h is 0.2, so this is 0.1, y0 is 1 and k1 is this, so this is 1.2 and this is 1.7, so this is 1.7. So the value is 0.2 multiplied by 0.1 plus 1.2 plus 1.7 and this is 0.6, K2 is 0.6. Now L2. And Z0 plus L1 by 2. So this is H, G of 0.1, 1.2, 1.7. Same argument for F and G. And this is 0.2 multiplied by 2 into 0.1 plus 3 into 1.2 plus 4 into 1.7. So this is equal to 2.12. This is the second order correction. Then going to K3 and L3 calculation. K3 is h f of x0 plus h by 2 y0 plus k2 by 2 z0 plus l2 by 2. So this is f, this is 0.1, y0 is 1 and k2 is this, so this is 1.3, this part is 1.3 and this is 1, L2 is so L2 by 2 is 1.06, so this is 2.06 and 0.692. 0.692 is the value of K3. Now coming to L3, x0 plus h by 2, y0 plus k2 by 2, z0 plus l2 by 2. Into 1.3 plus 4 into 1.7 and the result is L3 is 2.468. Now we have to calculate L4, K4, L4. K4 is h f of x0 plus h, y0 plus k3, z0 plus l3. So this is h, this is f of 0.2, y0 is 1 and k3 is this much, so this is 1.692. Z0 is 1, L3 is 2.468. And this is equal to 0.2 into 3.468 on calculation. This comes out to be 1.072. Now L4. The same argument, so we write it G at 0.2, 1.692 and 3.468. So this is 0.2 multiplied by 3 multiplied by 192 plus 4 multiplied by 3.468. 3.8696. Now, so y1 is y0 plus 1 upon 6 k1 plus 2k2 plus 2k3 plus k4. The values of k's are listed above, and when we put these values, we get y0 is 1 plus 1 upon 6, k1 is 0.4, 2 into k2 is 0.6 plus 2 into k3 is 0.692 plus k4 is 1.072, and all together on manipulation is giving 1.676 as the value of y2, y1 at x is equal to 0.2. Similarly, z1 is given by z0 plus 1 upon 6 L1 plus twice L2 plus twice L3 plus L4. Z1 is 1 plus 1 upon 6 L1 is 1.4, L2 is 2.12, L3 2.468, and L4 3.8696. On simplification, this comes out to be 2.412. So by this way we solve two first order simultaneous linear differential equation using Runge-Kutta method of order 4. So for H is fixed, this is the best solution that we can have using the Runge-Kutta families, methods of Runge-Kutta family. We could improve the result by dividing the step or by reducing the H value. We could find out, we could use H is equal to 0.1, so that from x is equal to 0 we first go to x is equal to 0.1, then use the values of x, y, z at x is equal to 0.1 to evaluate the value x, y and z at x is equal to 0.2. Then it will be a two-step process. It is expected that since H would be lesser than this, the two-step method would give you a more accurate result than this. You may perform a computer programming in which you divide, you set x0 is equal to the starting value and xn as the final value, and you divide the interval into n steps and provide n values from externally. As you increase n, h will decrease, and by this way you can check for the convergence of the result. Our main aim in this curriculum is to solve second order linear differential equation using Runge-Kutta method. In the next class, we shall describe how to solve numerically a second order linear differential equation using RK4 method. Basically, the method, what we shall do, we shall reduce a second order differential equation into two first order differential equation. That is why I have spent so much time in order to solve for two simultaneous equation, first order equation. This idea will be utilized in solving the second order linear differential equation.